Okay, so in question 17, looks like we've moved on to fluids at this point in the review. So a container is filled with two fluids, and the pressure of the system as a function of the depth below the surface is shown right. What is the ratio of the density of the less dense fluid to that of the more dense fluid? So it's sort of it's not a question you would typically have seen possibly before in the lecture. It's sort of trying to come up with a slightly different context for a very common sort of problem. So maybe I'll sort of draw. So it's reasonably common to have questions where you have a sort of container that has two fluids. So you might have the more dense fluid sort of at the bottom. And this is just a qualitative diagram, and then a less dense fluid sitting on top. I'm not sure how much of it is, but sort of a classic problem. What it uses x's, and you may have to find the pressure at a certain point in the fluid, knowing the height. So that's sort of the context that I was sort of working on here. So it is possible, I think, to maybe just read off certain values from the graph, but I sort of wanted to introduce a sort of slightly new idea about the slopes of these graphs. So it looks like, in a sense, there's a nice straight line here from 0 to 0.4, and then there is a kink in the slope here, and you've got a constant value here. So it looks like about 0.4 is where the pressure, in a sense, changes, and in a sense the slope of this graph changes. So in a sense we'll come back to thinking in a sense that we're going to define this as the depth below the surface. So it looks like we have 0.4 meters to where there is a kink here and a change, and I'll explain that in a second. And then it goes where from 0.4 to almost like 1.3ish. So the total depth is 1.3, so this looks about 0.9 meters. So, but if we think about, if we take any 2 points in the fluid where you have, in a sense, if I take just a general fluid and I label 0.1 at the surface and some 0.2 here, let's zoom in here. We state that the pressure of 0.2 equals the pressure of 0.1 plus rho GH, rho GD, I'll use D for depth. So I'll just rearrange this equation just slightly. So the pressure at 2 equals rho GD plus P1, where P1 is P atmosphere. So what I wanted to show you here is that what we're doing is we're plotting the pressure at some point below the surface, P2, as a function of the depth. And we can see here we get these two straight lines. So the pressure, in a sense, is increasing somewhat linearly, plus a constant, this constant being P atmosphere. So what I want you to see, in a sense, hopefully what you can see is that if we plot this on the y-axis as a function of x, then this quantity is our slope and this is our intercept. And hopefully you can see here that this is 101,000 and this should be at atmospheric pressure. So the slope of these lines is linked to the density of the fluid. That's sort of what I was trying to get at. So if we think about the slope at this time, will tell us the density, and then the slope this time will tell you the density. So we're looking for the density of the less dense fluid. So the shallower slope will be the less dense fluid. The steeper slope will be the more dense fluid. There's a greater change in the pressure for a given depth. So you can see that here that we have an increase in pressure with depth, which is what we learned in the lecture. So if we're looking for the the ratio of the densities we want to be considering the slopes. So if I use in a sense, maybe I'll just write a slope equals rho times g, then the rho will be equal to the slope divided by g. So if I want to write the rho 1 over rho 2, that will be the slope of 1 divided by g all over the slope of 2 divided by g. We turn this one upside down and multiply it. We're going to get slope 1 divided by slope 2. So what we can do for here is look at the slope for 1. It looks like there's a nice point here I can pick here at 104,000 at 0.4 meters. This intercept has to be atmospheric. So the slope, I have a change in y of 104,000 minus 101,300. So atmospheric pressure, these are in units of pascals, divided by a run or a base of 0.4, so delta y over delta x, all divided by, if we think about the here, again I got another nice point coinciding sort of up here at 112,000 at 1.2 and 104,000. So I'll do 112,000 minus 104,000 for my delta y, all over a base length of 0.8. So these are just, that's the slopes of both, and then we'll give you the densities, be linked to the densities, what we exactly linked to the densities. So the slope is equal to rho times g, and that should give you 0.68. So the density of the first fluid is about 70% of the density of the second fluid. And there are some other, I'm sure, methods. I think you can, knowing we have certain values, you may be able just to find the densities just from this equation and then do a division. But I just had written a question just as a new type of, sort of maybe a new idea of sort of linking the pressure and depth and representing it graphically and showing that if you're plotting as a depth from the surface, then you know the slope of the line can be linked to the density of the fluid.